Hello, everyone. Welcome to the webinar today. This webinar series will dive into the diverse applications of artificial intelligence across various domains crucial to achieve net zero objectives, including energy, transport, environment, agriculture, and food systems. Today, we are honored to host two speakers, Dr. Ashkan Lotfipoor from University of Surrey and Dr. Corentin Houpert from the University of Lancaster. So first, sorry, Lancaster. We will start our webinar series. The first speaker will be Dr. Ashkan Lotfipoor. So Dr. Lashford, the talk title will be Enhancing Energy Demand Forecasting and Data Imputation Using Deep Learning, Integrated Approach. And Dr. Ashkan is a data scientist with a strong background in applying machine learning to real-world problems. He holds a PhD in civil engineering from Harold Ward University, where his research focuses on deep learning techniques for time series forecasting and data imputation, particularly with the energy sector. Currently, Dr. Lotfipoor is a KTP associate at Surrey Business School, working with Cycle Confident to develop a business intelligence system. This project will empower Cycle Confident to advocate for cycling, secure more fundings, and ultimately contribute to a future where cycling is accessible and embraced by all. So let's welcome to the stage and good luck with this talk.
Hello, everyone, and thank you for having me today. Today, I'm going to talk about my PhD thesis topic, which was enhancing energy demand forecasting and data imputation using deep learning. I'm currently working as a KTP associate at Surrey Business School, and yeah, let's start the presentation. All right, so we all are familiar with the current global energy challenge that we are facing. The planet is warming and we need to stop that. And in order to do that, we need a transformation in energy sector. And that was the topic of my PhD. So energy forecasts are important for several reasons. They are essential for energy planning, grid stability, and integrating renewable sources. Of course, there are many challenges in energy demand forecasting, electrical energy demand forecasting. Missing data is one of those issues that happens because of the device malfunction or transmission errors in sensors. And having missing data in your data set for forecasting electrical energy leads to biased results and reduces the accuracy of your forecasting models. There are solutions and but of course they have some limitations. So one of the things that I tried to address in my PhD was to develop a data imputation methodology for energy demand data sets. So my aim in my PhD was to develop a novel system using machine learning for processing and predicting household electricity demand in the UK. I had several objectives, but the two that I'm going to explain today was to develop a missing value imputation model and to create a multivariate demand forecasting framework. In order to do that, I had 3 case studies. The first case studies was from Fintry, Scotland. We had a data set of 48 sites, and the data resolution was 30 minutes. The second data set was Cornwall LEM data set. We had 87 sites in that database. with 1 minute with 1 minute data resolution, but because I needed a variety of data resolution to test my model, I resample it to 5 minutes. And the last one was from Leader project. We had 21 sites with a resolution of 1 minute. On the right, you can see the average daily electricity demand across all households within each case study. And you can see they showcase different usage patterns. But it was my PhD thesis. It's a long thesis, and for today presentation, I'm only going to show you the results for Cornwall because we don't have time to go over the other two. So from each database, I choose one household based on a specific criteria that we had. So we have household A, household B, and household C. Today, I'm going to talk about the results from household B. And on the right, again, you can see the average demand and average daily demand, hourly demand in a day for the household. And you can see again that the usage pattern is different. So for the methodology, as I said, I tried to create a machine learning pipeline for forecasting electrical energy demand. And for that, we have several steps. We have data ingestion, we have data cleansing, data analysis and transformation, feature engineering, model development, model optimization, model validation, and you can finally serve your model with new data, and others can use it. But in my PhD, I didn't do that. I didn't serve the model, for example, in an app because I didn't have the skills. So I only focused on the model development part. So from data ingestion to model validation and having some results. In data cleansing, we have data imputation module that I'm going to talk about. Then the rest is going to be about the energy forecasting, like what kind of model that I've used, and etc., etc. Before that, as part of data cleansing and data ingestion, so we imputed some missing values with traditional methods. I handled outliers, we did normalization and things like that before going to data imputation. So a standard approach to data imputation research has 4 steps. We have data collection, we generate synthetic missing values as a second step. Then we develop an infilling algorithm, and finally, we can evaluate our results. So we had clean data and we needed to create missing values. On the right, you can see the algorithm for creating missing values. For missing values, we have 3 different mechanisms: missing completely at random, missing at random, and missing not at random. So based on the different mechanism, we had a different model to create those missing values into the data sets. For our thesis, for my thesis, I used 3 missing rates: 10%, 20%, and 30%. So we have 9 sets of results in total for each household. So let's start here. So this is the flow diagram for the methodology for data imputation. So first we have the pre-processing things that I explained earlier. Then we have clustering, and the output of clustering helps in handling the missing values, which I'm going to explain. Then we create the missing values, and then it's just like any other machine learning regression model. You just predict the values. So the novel thing about here, let me. So here you can see a time series with missing values. The M's are missing values. And if we want to have a machine learning model to infill that, we need to resample it into a regression problem. So that's what I've done here. So for example, to infill the M2, we need to have last four values, last four lagged values as an input into our model. But the problem is that we have missing values into our input data, and we need to address that before predicting the next values. So what is traditionally is done is people use simple methods like they use just the average or other simple statistical things to fill that M1. But what I've done is that I use the average demand value for the cluster. So I've done a clustering on the whole data sets, and I grouped similar households together. And my idea was to use a data point from similar households with similar pattern to infill that data because they behave the same way. So that's what I've done. So I estimate the average demand for the cluster, and I use that as a proxy values to infill the input features. Here you can see that. So for example, we have our target values with missing values, and the ones highlighted with reds are the ones that I use the average demand to infill. So that was the main thing about my topic. For the model, I've used a transformer network, and for training and testing, for training, I used the samples with known Y. So here we have some samples with known Y, some samples with missed Y. So I used the known Ys for training, and I used the missed Y for testing the model, and I had some results. So this is the clustering bit that I talked earlier. So this is from Cornwall. We had 4 clusters. This is the elbow method for choosing the number of clusters. I used k-mean. And for example, I used site 52 from cluster number 1, and I used the average of these clusters to infill the proxy values. And these are the box plots from each cluster. You can see that they have a different energy consumption. Yeah, so this is the methodology for the forecasting model. So again, we have 5 steps. First, I handle the missing values with the method that I mentioned earlier. Then we have the log transformation applied to the data set. Then we have an empirical mode decomposition module that breaks down and decomposes the load profile. Then we have a feature engineering pipeline that adds feature to the input space to helps the model. Then we have our model, which was a CNN LSTM neural network, and finally we have our forecasted values. And we also applied a log bias correction. Yeah. So the reason I use EMD, the reasoning behind it is that by applying an empirical mode decomposition to the signal, we can break it down into several IMFs. And the idea is that it's easier for the model to learn from these IMFs. You can see, for example, IMF from 10 to 15 are quite simple, so it's easier for the model to learn. But the first one are harder. But by doing that and applying a model to each of them, the problem becomes easier to learn. And these are the different features that I've used. Of course, I've used lag observation. We have a time series data. I used some temporal features, like is it a weekday or is it a weekend or is it a holiday, things like that. What part of the day is it at that time? I had some statistical features, and I also had some features from Fourier transform over the last 96 values. So this is the overview of EMD and feature engineering. This is the model architecture that I've used. So as I said, we had some lag observation and raw lag observation from the data, and we also had some engineered features. So there is no point to apply a CNN or by LSTM onto your engineered features, because there is no temporal information or pattern in them. So what I've done is created a two-pronged neural network. As our my engineered features goes through just some dense layers, and they're finally combined with the result from the layers on lag observation. I had two CNN layers, some by LSTM layers, and then I combine it. I had some dense layer at the end, and we finally have our results. This is how the data is shaped and is inserted into the model. For the evaluation, I had mean absolute error, mean square error, and root mean square error. I've For the hyperparameter optimization, there are a couple of methods: grid search, random search, and Bayesian optimizations. I've applied Bayesian optimization with these ranges to select the hyperparameters of the CNN by LSTM model. Okay, let's go to the results. So this is after applying the imputation. After creating the missing values into the data sets, this is what we saw. So this is the missing values for Cornwall case studies with missing at random scenario with 20% missing rate. So this is how the data looks like before trying to infill the missing values. And this is our result. So we have three different scenarios: missing at random, missing completely at random, and missing not at random. We have three different missing rates: 10, 20, and 13. And these are the methods that I use as a benchmark to test my model. Of course, my model is has the lowest value. The transform model is right here. And you can see it performs incredibly well in comparison to other methods like MLP, random forest, CVM, soft impute, linear, or just using the mean value. And so the thing is that you can see that with the increase of missing rate, other methods shown an increase in error. But the thing with the transformer model is that it almost has no reaction to it. So that's a really good thing for higher missing rates ratio. But the thing is that we're not trying to create a forecasting model, a regression model that we are going to evaluate the result with root mean square error. For imputation, you need to create values that are from the same distribution of the original value. So that's the objective. So to do that, we did two things. First, we plotted the distribution for all of the methods and saw that our model has had the closest distribution to the actual values. That was the first test, but we only did that for missing completely at random and missing at random. Missing not at random, there is some reason behind why it's missing. So you don't need to show it that your result matches the original data sets, because it would not in the real world. The second thing that we tested was autocorrelation plot. And again, we saw that our transformer value has the closest between others. Of course, others showed good performance, but for example, here you can see that our transformers and the actual values has the closest autocorrelation. So that was a really key thing to evaluate. Let's go to the forecasting model. So I tested my model for 4 forecast horizon, 5 steps, 6 steps, 10 steps, and 15 time steps in the future. And again, you can see that, so it was decided that 5 is the longest forecast horizon that my model can predict into the future based on the numerical results, but also from the graphs that we plotted. You can see for 5 and 6, it's really close, but if we increase the time steps, the error increases. These are the results from forecasting. So the benchmark was random forest and LSTMs, and of course our model is this one, EMD, CNN, LSTM. We tested for 2 scenarios, without feature engineering and with feature engineering, because we wanted to see if feature engineering has an impact on the result of the model. And of course, our model has the best performance among these benchmark methods. Then all of the models with feature engineering has a better performance in forecasting. The EMD, CNN, LSTM, in comparison with the model without the empirical mode decompositions, has the uh, lower error. So it all showed that the methodology that we have developed, it worked. And yeah, that was the main thing that we found out. These are some other examples from the forecasted results. I did some other studies, so I wanted to see the impact of number of IMEFs I've used. So we plotted this. This is the RMS of developed model in terms of number of IMFs used. For example, here I used only 2. Here I used 4, 5, 6, etc., etc. Of course, using more IMFs decreases the error, but also adds to the computational expense of running the model. So it was decided that 6 is good enough in both accuracy and computational expense and for the model. Another thing was to see was the forecasting error for each IMF, and so number 1 to number 4 has a more chaotic signal, so they are harder to predict. But as we increase the number of IMFs, they become simpler and they are easier for the model to predict. So that was the main conclusion from this analysis. So let's wrap up the presentation. So for the conclusion, so we developed a machine learning pipeline to both do the data imputation and forecasting of electrical energy demand in UK. We developed a transformer network for data imputation. We address missing completely at random, missing at random, and missing not at random mechanism with high precision. For example, our methods compared to traditional methods showed a 57% improvement. And the unique attention mechanism that is inside transformer networks accurately predicted the outcomes from lengthy sequences. So that was one of the key conclusion. Again, for our forecasting model, CNN LSTM model, the results with feature engineering and EMD were quite good in comparison to other methods. And of course, we had some challenges in predicting peak values for longer horizons, but this suggests area for future improvement. We provide a comprehensive tool for energy provider and policymakers, and we try to improve data quality and to help them to enable a better planning. The end-to-end framework that I've developed aids in shaping energy usage, preventing outages, and supporting data-driven decisions. Some suggestions for future work, like applying the transfer learning to adapt the model to households with diverse consumption patterns. That was one of the key area that we wanted to focus on in future. Thank you for listening, and yeah, if you have any question, please ask him away.
Yeah, thanks for the presentation. It was quite interesting. Is there any questions?
So there is no questions in the chat. I would like to remind everyone watching us live on the YouTube channel, you need to sign out by your Google account, and then you can post your questions and it will reach us directly in the broadcasting software we are using. While we are waiting for questions, I would like to ask you first, very good talk, Ashkan. I enjoyed it.
Thank
And
you.
it's very clear. I would like to ask you about what kind of structure for missing data in real data sets is observed. Is it more like, I do understand missing at random, but the two other techniques, I don't understand them. Could you can elaborate a little bit what are these and how they relate to real case scenario?
Sorry, your voice kept interrupting. Could you repeat your question because I didn't really hear that.
I am sorry. I'm connecting from far away overseas, so my voice is really might be tricky. So my question is, what is the structure of missing data in real data sets?
Oh, so in general, all three can happen, but from my perspective and from the data set that I had, missing at random was the main thing. But the thing is that I had clean data sets. Most of them had, very clean data set with all of the values present. But those that had missing values, I think the main reason for them was sorry, I said missing at random, but missing not at random, because the issue for missing values in energy demand is usually the sensor inside the house is turned off. Something happens to the sensors that creates long outages into the data. So that's the main mechanism in energy demand data sets.
And that's for multiple hours or maybe multiple days.
Yeah, until it solves, yeah.
So, but in most of the cases you assumed 1, 2, I don't know, what was the maximum length of missing portion of your time series?
So that we were considering two approaches. One was to address it in just creating continuous missing values, or just singles values that are missing. So that was one of the approaches that we considered. But the other was that to consider the missingness mechanism, like missing completely at random, etc. And we decided to do that. And for that, we couldn't specify the length of the missingness. What we could do was the missing rate of the data. So, and as I said, I used 10%, 20%, and 30%. And 30% is the maximum that we could logically, consider for the data before the data considered useless. Yeah.
Thank you. Minjia, the floor is yours. Do you have any other questions?
Yeah, I just have a very general question. I see that you heavily focus on the energy domain. How do you think this methodology is it easily transferable to other sectors, or needs a lot of adoptions to this domain specific?
Great question. So the idea from the beginning was to develop a model that can be used in other domains. So if you saw in my presentation, we only use the energy demand data. We didn't use any other data related to the building or the weather data, climate data, precipitation, things like that. We only use the just the signal from the building, the electrical demand, and that enables us to use the model with other type of time series data. So if you have a time series data you can try to implement this methodology with. Of course, you might need to tweak some details into the model, retrain it, things like that. But I believe that it can be easily transferred to other domains, which I've already done. I've used it for river flow forecasting in another project. So yeah.
I see. Yeah, thanks.
So I think we are running out of time, but I have a very pressing question I would like to ask you before we thank you again for your interesting talk. My question is about uncertainties and errors in time. What's your view about long-term time prediction as we move far away from our data? And do you have a vision to extend your work to do somehow uncertainty estimates?
So as you saw, I try to forecast longer forecast horizon, like 16, 15 time steps, which was, for example, 3 hours or 5 hours, something like that. But the model couldn't perform well. And I think the reason was the model itself. So during my PhD, I've done the forecasting model first. Then I learned about transformers and I did that data imputation thing. But the transform model is much more capable on handling, temporal relations, temporal patterns into the data. So I think if we use a better model like a transformer model with right sets of hyperparameters, we can forecast longer periods of time. But of course, as you increase your forecast horizon, your errors stacks on top of each other, and it's become harder to predict. So yeah, I don't have a clear answer to that. It needs to be a study, but it's a fascinating thing to do.
Thank you, Ashkan.
Yeah, thank you.
The floor is yours.
Yeah. So thank you again for the talk. We now will move on to presented by Dr. Corentin Houpert. Dr. Corentin Houpert is currently a postdoc researcher in AI at the University of Leicester. His work focuses on generative methods for net zero emission and astronomy simulations. He has a background in mathematics and applied mathematics. He holds a PhD from Ecolopolitics entitled Inverse Problems for Stochastic Neutronics. Let's welcome Dr. Houpert, and the floor is yours.
Okay, thank you a lot, Menja. So today I will be presenting our work on physics-informed autoencoders in order to fill missing values in the net ecosystem exchange measurement. So this is a joint work with Mohammad Sadzia, Ashkan Lotfipoor, Noel Clancy, York Kaduk, and Aiko Balster. So first of all, I will introduce you what are the ecosystem measurements in the context of the digital twin project AI for Net Zero. Then I will introduce you the NE dynamics with the nighttime and daytime model. Then I will introduce first the nighttime model, then the daytime model. This model depends on air temperature and radiation. So I will introduce the dependencies and explain how it fits into the model. And finally, I will sum up the NE dynamics as a stochastic differential equation. Finally, I will introduce the physics-informed autoencoders architecture in order to fill the missing values in the net ecosystem exchange measurement. And finally, I will conclude. So first of all, what is the project AI for Net Zero? So we know that about 11% of the agriculture, the UK net greenhouse gases emission are from the agriculture and land use. 7% comes from ruminant farming, including cattle and sheep. 4% come from the agricultural use on drying peatland. So the aim of the digital twin project AI for Net Zero is to answer some questions of the farmers, the policymaker, or the landowner. So As an example, a farmer can ask himself, how growing different crops and or cover crops in the winter have an impact on the CO2 emission. What will be the future climate impact, change impact? As example, heat wave, drought, or cold spell. What would be the impact on the land management choices such as tillage or crop rotation? Should we buy or sell a plot of land? So a digital twin is a digital representation of the environmental system. It updates itself based on continuous data flows. Its data lead to actionable information that fits back on the environmental land management practices and choices. And the digital twin is intertwined with the physical twin. So in this context, we are using flux towers that are measuring the CO2 emission at field scale. They measure a quantity that is called the net ecosystem exchange that measure the CO2 exchange between the atmosphere and the main carbon pools. So here you can see a flux tower with a sonic anemometer as example. So at field scale, flux towers are used in order to measure CO2 emission. The net ecosystem exchange is deduced from the vertical component of the flux. So you know that the wind speed has an overall tendency. So this is the big arrow in violet. And inside the overall tendency of the wind, you have small and big vortices. So people are doing alpha hourly measurements, and in fact, so the flux tower is capturing what's going out in its back regarding the direction of the wind, and it's doing some measurements over some ellipses where you take the mean value on a foci. So you obtain a heavy tail density. And so people compute the vertical component of the flux as the covariance of the vertical component of the wind speed with respect to the concentration of the quantity of interest. So it can be CO2 or methane. So what does the measurement look like? So here you can see that this is for a day, and there we have something like 3 points, and this is for we have too many missing values. So I will show the next one. So for a week, you can see that you have the flux that is measured in blue. You see that there are something that is noisy, and you see that the computation that are made by Joule, so which is the Joint UK Landscape Simulator, which is a big code of numerical analysis that computes the solution of ordinary differential equation. And so you can see that you have some tendency, some periodicity that we capture with Joule, but not the peaks. So the same goes for at monthly scale, but you see that we don't really fit even the mean value of the flux right now. So Joules, it does not feel like in this configuration with the flux tower. And you can see you still have the periodicity, but not the mean value, neither the spikes on the seasonal scale. So in our context, we will use physics-informed autoencoders in order to generate measurements to test the machine learning algorithm and quantify the associated uncertainty. So you can see here in orange that we have some missing values. No, we have some measurement in orange, and in blue we have the missing values that are filled with the marginal distribution samplage, which is an algorithm that is already used in flux towers. And I represent the confidence interval in shaded or orange or blue. So this is for a day, and we want to do the same for a day, a week, a month, and a season. So what is the net ecosystem exchange? So the net ecosystem exchange represents the net exchanges of CO2 between the ecosystem and the atmosphere. It is decomposed in two components. The first one is the ecosystem respiration, and the other one is the gross primary products, which represent the photosynthesis. So we have two models, one for the nighttime and one for the daytime. So during the nighttime, we know that the gross primary product, which represents the photosynthesis, is assumed to be 0. So we have only the ecosystem respiration. So we have our night. We have we have an exponential term. This is called an Arrhenius law type law, and so we have the air temperature that have an impact on the ecosystem respiration, and this is composed of a positive coefficient that is the base respiration at the reference temperature Tref, and we have also another parameter that is the temperature sensitivity that is fixed for the whole year. The base respiration is updated every five days in order to fit to the model and to avoid some noisy or weird behavior of the measurements. And it uses 15 days history. So you have the air temperature that has an impact on the ecosystem respiration, and you have some fixed temperature also. So to make the link between the nighttime and the daytime model, we say that as solar respiration is a very large component of the HARICO, and it continues from night to day, the temperature sensitivity of the respiration in knots might not change. On the other side, for the day, we have the gross primary product, which is assumed to be some rational fraction of the global radiation. So we have GPPs assumed to be alpha beta times Rg over alpha Rg plus beta, where Rg is the global radiation, and alpha is the canopy light utilization efficiency, and beta is the maximum CO2 uptake of the canopy light at light saturation. So all in all, for the daytime model, we add the ecosystem respiration and the GPP, the gross primary product, with all the parameters that I listed before. So this model depends on the air temperature. So to give you an insight about how evolves the temperature over a day, you know that the temperature evolves as a function of the season. So in the winter, you have smaller days than in summer. So this has an impact on the ecosystem exchange. And you know that the sunrise, when the sun is rising, the temperature should be minimal, and then at 12 p.m. you should have the maximum temperature, and then when the sun sets, you should have also the minimum temperature. So it gives you some kind of cosine function that gives you an insight about what is the temperature, but you need to take into account the noise. There are some other parameters that will have an impact on the temperature. On the other side, there is the solar radiation we need to take into account. So I won't dive into the details here, but you have to take into account short wave and long wave. And there is the absorbance of the Earth that is on the field. So this is also something that has an impact on GPP. So to sum up, we know that since we are dealing with physical measurement, there is a noise of observation. So we know that from the literature, NE is given by a mean value plus a noise, and the mean value is given by the derivative of NE with respect to the time. So since we have NE is equal to HARICO minus GPP, we need to differentiate HARICO with respect to the air temperature times dt dtr over dt minus d over drg of GPP times drg over dt, and we know that we have some noise that would be different for the night and the day. So we check that empirically. And here is what we did. So I will be talking from the left to the right. So at first, we have the measurements. We have the parameter that define the SD for a day, as example. We have the NE values, the force symptom that is corresponding to the differential equation associated, the air temperature value, the radiation at time t. And then we encode this data into a latent space. So we have a latent variable that are represented. And then we decompose and sample from the latent space with some deterministic decoders that will be sampling the parameter of the stochastic differential equation, the variation of the air temperature over time, the variation over the radiation, the force in term, the net ecosystem exchange, and we will add also a stochastic sampler in order to decode the noise value. So since this is a Gaussian distribution, we only need a mean and a standard deviation. Then we feed everything into the stochastic differential equation. Then we take the sum, and we are able to give what's the next NE value. So since we are dealing with some deterministic quantity, we will consider the mean square error for that. And then for the stochastic process, we will consider the maximum mean discrepancy. And finally, so our baseline is the random forest robust algorithm. So this is the third line counting from the top. So you see that we have some mean value that is captured well, but not the standard deviation is pretty high, and we don't match with the spikes. The last picture coming from the top is XGBoost, so this is also performing the same way for a day or for a week as the random forest. You can see that if we use the autoencoder without the physics, we are able to capture the mean value on the spikes well. We have a small standard deviation, but it is not interpretable in terms of physics. So if we add the physics on top of that, we have almost the same result as the autoencoders, but we are a little more accurate. So this is interesting, and we have the same conclusion for a month or a season. So this is interesting because we are considering artificial scenarios where we remove some values and we try to fill them. So we see that in this case also for a month or for a season, we still have some interesting results that capture well the mean value and the noise. So all in all, we presented a physics-informed autoencoder that combines empirical and nighttime and daytime NE models with a Gaussian noise model, which improved the robustness and the accuracy in filling gaps and forecasting NE. So our contribution includes the introduction of a new stochastic differential equation for the net ecosystem exchange measurement, combining daytime and nighttime model with the Gaussian noise. We also demonstrate that the physics-informed autoencoders improve gap filling robustness compared to the state-of-the-art methods, handling gaps from months to years. And we are able to accurately predict stochastic differential equation parameters that enhance the interpretability. Thank you very much.
Yeah, thank you for the talk. It's very interesting. Let's see if there's any questions.
There's no questions in the chat. I remind the viewers online, please sign into Google first, and then you can post the questions. And while we are waiting for a question, I would like to ask something similar to what I asked Ashkan. In the real data sets, what is the patterns of missing intervals observed? Or do you have access to a real data set where the communication was interrupted for a part, or storage failed, or?
So it comes from the source of so you can have some spikes that will be corrected by some software of the flux tower. You can have some energy shortage or some months where there is some lack of funding. So this can be the source of missing values.
Okay. So, but the like if there is a missing that values, did you, for example, plot the distribution of the duration of missing values if you are on minute, like data frequency? What is the average missing um, duration of your data, and what is the distribution of that? Or if you are working with monthly data sets, did you do that exercise, or?
No, so we did not study that way the distribution of the missing values. That's true.
Yeah, fair enough. The second question is in terms of it's always amazing to see people bringing back physics, because this is where we argue that physics is a compressed form of patterns we observe, and it usually have a generalization ability. By meaning, if you have partial differential equation and you validate that, with, then you can at certain points you can literally extrapolate. Um, when you presented the results between an autoencoder data driven versus physics informed, in terms of generalization, was the test on randomized validation data or entire validation data, which is the entire data series? And then the follow-up question, was these in between our training data or outside our training data? Can we show that physics add generalization? This is where the bottom of my question.
So I don't really know how to answer that question.
So let me reiterate, like let's assume that we are just dealing with data-driven approach, and we have data sets within the range between -10 to 10. And if we are using random forest outside the domain, it will be constant. Outside the data, till -20 and and +20, it will be constant based on the random forest prediction. If we are dealing with a Gaussian process regression, pure data driven, we will see that the uncertainties go larger in the extrapolation parts, and the extrapolation value will be the mean of our training data. We have done experiments on the data-driven approaches, and we know how it fails in an extrapolation regime. The question is, we promote physics informed because it has better generalization, but do we know how it behaves in the generalization regime or not?
No, I don't really know. Or we did not study the generalization, so it is focused on this application, and we were trying to. I think we need to find some other time series data set to test the generalization.
Yeah. So specifically for the data set you used, it is the validation data set is the random subset of your.
So we computed. So yeah. So for the data set we have a random missing values, but we can have some. There is an history. I know regarding the land management. So maybe people have some history also of what happened to the flux towers that could explain what the missing values come from. And so what we try is to randomly input or output some values and to reconstruct them, knowing that we know the parameters. So we are able to sample the parameters of the stochastic differential equation for the lifetime model. Yeah.
Thank you. Very interesting. Minjia, do you have any questions?
Thank you. I just have a general one. I just want to get some of your comments about like pure data-driven approach versus physics-informed approaches. Like, do you think is there like a potential for like if you collect more data to compensate the physics part, or do you think it is essential like for a lot of applications, or it's very application specific?
So our work shows that it is very application specific. I don't know much more about other application domain.
Yeah. Okay.
Thank you.
So,
Thank you for.
yeah.
Sorry.
So because in fact the question is, okay, we can take the mean value, which is already a good approach. Random forest is already very good also for the daytime. We can our algorithm enables us to fill the literature missingness regarding the nighttime model. And in fact, this is a stochastic differential equation with two parameters and a Gaussian noise. So it's quite simple, and it will depend on the model if there is something that is more physics that is more complex. If the noise is composed, you need to maybe to consider something that is more refined that will take into account the moment of the distribution. And if the distribution is quite noisy, then it will be difficult. So there are many kind of uncertainties that can arise from the model, from the noise sampling. So what I discussed around me regarding it seems that random forest is a very good algorithm, generally speaking. And maybe if you, so the question, so I discussed with someone on that is dealing with else data. So she was telling me that she's using random forest and this is already a very good algorithm. The question for her was how you use the field missing values. And I think using the physics would make more sense. But this is synthetically added. You can have some interpretation of that. But the thing is, if you have missing values and you have side effects that you want to predict, then you erase these side effects. So
Thank you.
there are some counterparts.
Yeah, thanks for the answer. So due to time constraints, I think we'll end the question session for now. Do you have anything to add? Or
So I will take it from here. Thanks to our two speakers today, Ashkan and Corentin. Thank you for sharing your very interesting work. And thanks to the host of today, Minjia Zhu from the University of Manchester. And I would like to announce the next seminar, which is scheduled at the same time, 2 p.m. GMT time, UK time, on the 28th of January. And next week, we are pleased to have Professor Lorraine Whitmarsh from the University of Bath, who will take us on a different journey, more about behavior change for net zero. So it's a very exciting talk. We are looking forward to the talk by Professor Lorraine, and I would like to thank everybody who has tuned today and the speakers and my folks. Have a good day, everyone.
thank you.
Thank you.